Hello everyone, welcome to lecture 23 in physical organic chemistry, in which we are now studying the pericyclic reactions. In our previous class we had seen the examples and various classes of electrocyclic ring closing and ring opening reactions, and we had seen the selection rules previously with respect to various pericyclic classes. And now moving ahead, we will see the cycloaddition reactions. We will focus more on the theory in this particular class, and we will see a couple of examples. As always, this particular lecture has been sourced from the textbook written by Professor Shankaraman from IIT Madras on pericyclic reactions and his lecture notes. And most of the material that I have taken in this lecture comes from this particular textbook. Alright, let's go on to now defining what is a cycloaddition reaction. A cycloaddition reaction, by definition, is the union of two smaller independent pi systems where sigma bonds are created at the expense of pi bonds. And obviously, as the name suggests, it's a cycloaddition. That means these are essentially ring forming reactions. They are mostly pericyclic in nature, but there are exceptions. There may be cycloaddition reactions that may proceed stepwise, especially those which are electronically biased. In these cycloaddition reactions, both intramolecular and intermolecular versions are abundant. You find several examples of both classes. Listed here are some of these examples in which you have a 2 plus 2 cycloaddition, you may have a 4 plus 2 cycloaddition, you may have 4 pi cycloaddition, you may have a 2 pi 4 pi cycloaddition of this kind, and sometimes this is also labeled as a 3 plus 2 cycloaddition. We'll see the classification in a minute. This particular typical example we are going to see later is a 14 plus 2 pi cycloaddition reaction. So the classification of cycloaddition reactions goes in this way. These are often referred to as M plus N additions. When a system of M conjugated atoms combines with a system of N conjugated atoms, it is called as an M plus N cycloaddition. So a system of this kind would be known as a 2 plus 2 cycloaddition. This would be known as a 4 plus 2 cycloaddition. This would be known as a 3 plus 2 cycloaddition. There's another classification which is based on the number of pi electrons involved in each component. And as you can see here, what is written here is that particular classification. So this would be a 2 pi plus 2 pi cycloaddition. This would be a 4 pi plus 2 pi cycloaddition. This would be a 4 pi plus 4 pi. This would be a 2 pi plus 2 pi, and this would be a 14 pi plus 2 pi. There is an opposite of cycloaddition that is called as a cycloreversion reaction, and this is the complete opposite or the reverse of the cycloaddition. The stereochemistry of cycloaddition reactions is dictated by orbital overlaps. In the cycloaddition reaction, the pi system may be attacked in one of the two distinct ways, in the suprafacial approach or in the anterofacial approach. Sometimes we call this as a syn addition or an anti-addition. If the pi system is attacked from the same face, then the reaction is suprafacial on that component. We have seen this definition earlier. If the system is attacked from opposite faces, then the reaction is anterofacial on that particular component. For example, if you see a 2 plus 2 cycloaddition of ethylene to form cyclobutane, then it is a 2 pi suprafacial plus 2 pi suprafacial process. Whereas the thermal Diels-Alder reaction is defined as a 4 pi suprafacial plus 2 pi suprafacial process. Now, let us consider these particular transformations. We know from our literature and previous studies that with butadiene you can combine maleic anhydride in a very nice reaction which is thermal, but under the same conditions you cannot combine just ethylene. So there are certain rules involved in cycloadditions. Similar to what we saw in electrocyclizations, there are certain sets of rules that govern cycloaddition reactions. Also, if we know that certain olefins can be combined under thermal conditions to give you cyclobutanes. But we know that such reactions take place at very high temperature and are non-concerted. So although this is a cycloaddition reaction and it is thermal, it is a non-concerted type of reaction, therefore cannot be classified as a pericyclic transformation. On the other hand, we know that the photochemical variant, a 2 plus 2 cycloaddition, is a concerted reaction. So that's a pericyclic transformation. Let's now consider the frontier orbital method of analysis for the cycloaddition reactions. As you can see here in the diagram, the homo-LUMO interaction for a 2 pi superficial, 2 pi superficial and a 2 pi superficial and a 2 pi antrafacial cycloaddition is given here. In the first type, the reaction between two ground state ethylene molecules in the supra-supra mode is shown. So the HOMO of one of them has to combine with the LUMO of another, by definition. So you can see here that the symmetry of the HOMO and the LUMO are not the same. Okay, and the HOMO-LUMO interaction leads to an anti-bonding destabilization. Therefore, the superficial mode of 2 pi 2 pi cycloaddition is thermally forbidden. What happens when we consider this in a 2 pi superficial 2 pi antrafacial process in the ground state? That means in the thermal reaction. We can see that now both of these are actually bonding interactions, right? So the process 2 pi superficial plus 2 pi antrafacial in the ground state is clearly bonding in nature. That sorry, I was supposed to mention on this particular diagram. Okay, so you can see here, not in this particular case. Okay, so you can see here for a antrafacial superficial, this particular overlap is clearly bonding in nature. Coming back to this particular transformation, you can see a superficial in the excited state, that means in the photochemical reaction, gives you a bonding overlap. That means the process which is forbidden thermally is now permitted photochemically. So in this particular diagram, we are actually seeing the excited state for one of the ethylene and the LUMO for an ethylene which has not been excited. Okay, so now since this is the singly occupied molecular orbital, it becomes the HOMO in the excited state because one electron is transferred to that particular orbital. Therefore, we have now this as the HOMO for the excited ethylene. And we can see that there are two bonding overlaps in the excited state, which is therefore a photochemically allowed process. Coming back to the antrafacial superficial overlap, we are saying that there are bonding overlaps between these two orbitals, as you can see here. Let's see whether this is permitted or not. Now, this is a symmetry allowed in the ground state, obviously, but in order to accomplish such an antifacial overlap of orbitals, we can see here in this diagram that the two pi systems must approach each other in a perpendicular geometry. That means they are almost orthogonal to each other, as opposed to the parallel approach in the case of pi 2s and the 2 pi s mode. So therefore, there are geometric and steric constraints which do not allow such a process to take place. So even if it is permitted under thermal conditions, examples of thermal cycloadditions of simple olefins of the type 2 pi s plus 2 pi a are very rare. So in the photochemical mode, as we go back, the interaction between the HOMO of the excited state ethylene, like I mentioned earlier, and the LUMO of the ground state have the same symmetry. And therefore, the HOMO-LUMO interaction results in a bonding stabilization of the transition state. Therefore, the 2 pi s plus 2 pi s mode is symmetry allowed in the excited state and therefore is permitted under photochemical conditions, as you can see from this particular diagram. Now let's consider for a 4 pi s plus 2 pi s system. As we can see here, the ground state HOMO-LUMO interaction is what we are looking at. So you can see here in this particular case, if we are considering the HOMO of butadiene with the LUMO of ethylene, or the LUMO of butadiene and HOMO of ethylene, in both the cases, the 4 pi s plus 2 pi s is having the same symmetry. Okay, the orbitals are of the same symmetry and they are interacting. It results in a bonding stabilization of the transition state. Therefore, this cycloaddition is thermally symmetry allowed. What happens under the photochemical conditions? Under the photochemical conditions, suppose now you have excited butadiene. In the excited state, the side 3 becomes the HOMO. So the overlap between the side 3 of butadiene with the LUMO, that is the ground state LUMO of ethylene, gives rise to an antibonding overlap. Therefore, this is symmetry forbidden and is disallowed. We'll now see the orbital correlation method for the two cycloadditions, for the 2 pi s plus 2 pi s cycloaddition. For the 2 pi s process, there are two planes of symmetry, as we can see in this diagram, and these are conserved throughout the reaction, and we identify these planes as sigma 1 and sigma 2, as we can see in this particular diagram. So with respect to these symmetry elements, the symmetry properties of the molecular orbitals of the two interacting ethylenes as well as cyclobutane are shown in this particular diagram. We can see here, according to the energies, we have arranged these sets of orbitals. One is a symmetric with respect to one ethylene, symmetric with respect to other ethylene. One is symmetric antisymmetric with respect to each other. One is antisymmetric symmetric, the other is antisymmetric antisymmetric. Okay, this is with respect to the sigma 1 sigma 2 plane. Okay, now in the case of the cyclobutane, again we are arranging them according to the energies. So symmetric with respect to one plane, antisymmetric with respect to other, symmetric antisymmetric with respect to the other, and then antisymmetric. Okay, all right. So now the symmetry of the molecular orbitals in the ground state of the starting material correlates with the symmetry of the excited state product. That means it is with respect to this particular orbital. So this symmetry is correlating with respect to the excited state of the product. This, obviously, if this has to happen, it will be allowed only in the excited state, because obviously we are crossing the non-bonded level. So, as we know from our previous studies, this will be permitted under photochemical conditions only. Let's now go to the 4 pi s plus 2 pi s process. You can see here we do not have two planes of symmetry. There's only one plane of symmetry here. We call that sigma, and it is maintained throughout that particular process. So this particular plane passes vertically from between this particular space. Okay, if one has to observe it in 3D. The symmetry properties of the molecular orbital in the ground state now correlate with each other without crossing the non-bonded level. So you can see here we have arranged in this particular column the orbitals with respect to increasing energy. So you have psi1 for butadiene, followed by pi for ethylene, followed by psi2 for butadiene, psi3 for butadiene, pi star for ethylene, and psi4 for butadiene. And then we have the cyclohexene. So we have the sigma 1, sigma 2, pi, pi star, sigma 3, sigma 4. Okay, and we can see that the symmetries are correlated in the ground state without crossing the non-bonded level. Therefore, this process is thermally allowed in the ground state. If we have to see the aromatic transition state model by Dewar and Zimmerman for the 4 plus 2 cycloadditions, then we can see that this shows a Huckel type aromatic transition state. There are no phase inversions. Therefore, it is a 4n plus 2 system, no phase inversions. Therefore, this is thermally allowed and photochemically forbidden. What I want you to do now is that you satisfy yourself whether the 2 plus 2 cycloaddition in the supra will be thermally or photochemically allowed under the Dewar-Zimmerman model. If we have to see this by the Woodward-Hoffmann generalized orbital symmetry rules, then we can see here in the supra-supra approach in the ground state, okay, we can see the HOMO and LUMO have one antibonding overlap in the supra-supra. Therefore, the 4q plus 2 supra, okay, we have two components, and the 4r we have 0 components. Therefore, this is not allowed because this is even in the ground state. Alright. In the suprafacial anterofacial approach, we can see here that there is one 4q plus 2 supra, okay, where q is 0 and 4r antera is 0. Therefore, the total number is 1. The number is odd. Therefore, this is allowed in ground state. But obviously, we have seen that this is geometrically and sterically disfavored. Let's analyze the Woodward-Hoffmann generalized orbital symmetry rules for the 4+2 cycloaddition. So in this particular case, as you would notice, we are considering in this particular analysis the HOMO of ethylene and the LUMO of butadiene for our simplicity. In first case, if it's a superficial, then we can see here that the 4q plus 2 for the superficial is 1, whereas for the antifacial the 4r is 0. Therefore, the total is 1 and therefore this process is allowed in the ground state. Next, if we consider the 4r antifacial and the 4q plus 2 as antifacial, this is 1. Therefore, again, this is allowed in the ground state. If we see the antifacial and superficial, both of these are 1 each. The total is 2 and it is even, therefore it is not allowed in the ground state. For the superficial antifacial overlap, we can see that the 4q plus 2 superficial is 0. There is no component because this is antifacial here, and for the 4r antifacial we are seeing that there are no components, therefore this is 0. It is even, therefore not allowed in the ground state. So we can generalize the Woodward-Hoffmann rules for cycloaddition reactions. For number of electrons which are p plus q, if the total is 4n, then the p pi s plus q pi a or p pi a plus q pi s is thermally allowed. Okay, the supra is forbidden, whereas in the photochemical the p pi s plus q pi s is photochemically allowed. On the other hand, if the p plus q is 4n plus 2, then the p pi supra plus q pi supra is thermally allowed. On the other hand, in the photochemical process, the p pi s plus q pi a or antera is photochemically allowed. Okay, so excuse me, what we need to remember is the allowed processes and the forbidden processes shall automatically follow. Alright, we had said that the thermal 2 pi antera and 2 pi supra are geometrically and sterically not feasible. Although thermally, according to the Woodward-Hoffmann rules, these are permitted. But there are exceptions to this rule. And why these are exceptions? These are exceptions because of their bonding nature and the nature of their orbitals. So let's now consider the cycloadditions of ketenes, isocyanates and allenes. These can undergo a 2 pi plus 2 pi cycloaddition to give a 4-membered ring system. In the case of ketenes, the reaction is very facile when the ketene bears electron withdrawing substituents such as halogens and the ketenophile is electron rich. For example, in this particular case, you can see that the ketenes will bear electron withdrawing halogen substituents and the ketenophile, that is the olefin, will be electron rich. Why this is so facile? The electron withdrawing group lowers the energy of the LUMO of the ketene, and the electron rich olefins obviously have higher energy HOMO. So higher HOMO, lower LUMO, a better overlap, the better interaction between them, therefore more facile the reaction. Now the molecular orbitals of the ketene, and we can see the HOMO-LUMO interaction between an olefin and the ketene is shown here. As you can see here, if one has to find out the energy levels for and the coefficients of orbitals for the HOMO, we can see that the coefficients are higher at the ends, whereas the coefficient is the largest at the central carbon in the LUMO of the ketene. So, the LUMO of the ketene is therefore a low-lying carbonyl pi star level, and it has the largest coefficient at the central carbonyl carbon. One end of the pi bond of the olefin, which is preferably having the largest coefficient, that means it is the electron rich end in the case of unsymmetrical olefins, it starts to interact with the largest lobe of the central carbon of the ketene. What we are talking about? We are talking about this particular interaction. This interaction will dictate the regioselectivity of the ketene cycloaddition. At the same time, the other end of the olefin interacts with the terminal carbon of the ketene. Now in this particular case, this was the py orbital, whereas in this particular case, this is the pz orbital. These two are orthogonal to each other. Therefore, with respect to the ketene, the addition is antifacial. With respect to the olefin, it is suprafacial. Therefore, according to the Woodward-Hoffmann rules, this is 2 pi antera and 2 pi supra cycloaddition and is thermally allowed. There's an alternative explanation to this particular process. Let us see that. Now we already know that the thermal cycloadditions between two alkenes do not work because the homo-LUMO combination is antibonding at one end. Okay, let's see this diagram once again. So if you turn the alkene at 90 degree in a way in which the HOMO of one will bind with the LUMO of the other, then let's first turn the HOMO of one alkene so that we are looking down at the p orbitals, okay, in this particular fashion. Okay, so there is bonding overlap at both the ends. Okay, these are orthogonal now. Now this looks very good. We have seen this particular arrangement. However, there is now also an antibonding overlap at this particular end. Therefore, whatever bonding overlap was there was nullified by the antibonding overlap. Also, we know that geometrically there is a problem. Sterically also, this is not a very good situation. If this particular species now has a p orbital at one end at the right angle, so that now both the orbitals of the HOMO can bond to this extra p orbital in this particular fashion. Then now there are 4 bonding interactions but only 2 antibonding. Therefore, the net result is a bonding interaction. Therefore, ketenes, isocyanates, allenes which possess this kind of an extra pi bond are perfect for these type of cycloadditions. If we have to look at it once again, then this is the way we are looking at it. So there is now a new interaction of this kind. Okay, so this is an alternative explanation for the cycloaddition of ketenes to olefins. So you can see here now with respect to this orbital, this is antifacial. With respect to the olefin, this is suprafacial. So this is pi to 2 pi s plus 2 pi a and therefore thermally allowed. What about the regio and stereospecificity for ketene cycloadditions? There are a lot of examples in literature which will tell us about the regio and stereospecificity of such processes. Unsymmetrical ketenes, will react with unsymmetrical olefins in such a way that in the product the bulky substituents are cis with respect to each other. As you can see in this diagram below, why is it? This is because there is a perpendicular approach to the two pi systems with two bulky groups as far apart as possible to minimize the non-bonded interactions, the steric interactions in the transition state, which will end up putting them cis with respect to each other in the product. Okay, so you can see from this diagram, if this is the approach, there is a large steric interaction in this particular case, whereas in this particular case, the steric interaction is minimized to certain extent, leading to this particular type of transition state. And if you flip this now and make it a proper cyclobutane, this will look somewhat like this, where the two large groups are now cis to each other. With respect to the stereospecificity of cycloaddition, if you see the reaction of cis and trans cyclooctane, you can see here the very high stereospecificity clearly indicates that there is a suprafacial manner in which the two olefins are interacting with the ketene. So the geometry is maintained and the relative stereochemistry is maintained in the product, which clearly indicates that there is a suprafacial interaction with respect to the olefin. How do you generate ketenes? Ketenes can be generated in a variety of ways. Most common method of generating a ketene is from acid chloride. So you can see here, if you use a base with an acid chloride, results in an E2 type of elimination, gives you a ketene. Ketenes are not very stable. They have to be used quickly and will decompose rapidly. From alpha chloroacid chlorides, if you can use a metal, in this case also you can use this type of elimination to give you this. This should not be a base, it should essentially be zinc. Okay, so you get a ketene in this particular case. You can use cyclobutenones and ring open them to give you alpha beta unsaturated ketenes in an electrocyclic ring opening process. You can also do this by using alpha diiso ketones. These alpha diiso ketones can be generated very easily using diiso transfer reactions, and we know if you either heat them or photolyze them, these lose a nitrogen molecule, thereby generating a carbene species. This carbene will rapidly rearrange to give you a ketene. The survival of these ketenes will depend on what the reaction medium is. If the reaction medium possesses nucleophiles that can attack the ketene will not survive. Okay, let's see some examples. So in this particular case, there's a very good application of the thermal 2-pi intra plus 2-pi supra process of ketenes. In this particular case, a bicyclo 3,2,0 heptanone has been obtained from the cycloaddition of dichloroketene to cyclopentadiene in a 2+2 cycloaddition. This has been taken further to synthesize two very important natural products, the cis-jasmone and a variety of prostaglandins. So in this particular process, first you generate this bicyclic structure, then reductively remove both the chlorines, gives you this ketone, which can now be rearranged under Baeyer-Villiger oxidation conditions to give you this particular lactone. The intramolecular cycloaddition of ketenes is synthetically quite useful. Usually it proceeds in high yields. If the ketene and the ketenophile are held together in a close proximity by a rigid tether. So this should not be very fluxional. If it is, then the cycloaddition is not very effective. Okay. The regioselectivity is determined by the substitution pattern on the olefin. The substrates in which the internal carbon of the olefin is more substituted, these will give bicyclo N20 alkanones. Whereas the substrates in which the terminal carbon is more substituted will give bicyclo N11 alkanones. The cycloaddition of ketenes is found to be sensitive to steric hindrance and electronic effects of the substituents. Usually it is observed that if the alkene is trans 1,2 disubstituted, it will give higher yields than cis isomers, obviously because of steric crowding. It has also been found that aldoketenes, what do you mean by aldoketenes? Aldoketenes means those ketenes that possess only one group at this particular carbon. If there are two groups at this particular carbon, then it is a ketoketene. This additional group, if it is present, will create steric hindrance. Therefore, the reactivity of ketoketenes is lower than aldoketenes. However, if you place an alpha chloro, or if the ketene is alpha beta unsaturated, then this is more reactive than aldoketenes because the energy of the LUMO is now lower in these particular ketenes. This is a fantastic example of an intramolecular ketene cycloaddition. You can see this starting material is alpha chloroacid chloride. In this particular case, triethylamine is used as a base and abstracts a proton from this allylic position to give you this particular ketene. So if this is H and there is a base, this abstracts in this particular fashion to give you the ketene. This ketene now undergoes an intramolecular cycloaddition and gives you this beautiful bicyclic structure depending on what is the substituent. If R is equal to H, then it undergoes this kind of a cycloaddition to give you a fused bicyclic structure. If R is equal to methyl, it gives you a bridged bicyclic structure. Similarly, you can see here, this is also a beautiful example. In this particular condition, diisopropyl ethyl amine abstracts a proton from this particular allylic position, giving you this particular ketene. This now adds on to this olefin to give you a fused tricyclic structure. Ketenes can add on to variety of substrates. They can dimerize to give you species of this kind. They can add to carbonyls in a 2+2 fashion. We already saw 2+2 additions with alkenes. They can also add in a 2+2 fashion with imines, and they can add in a 4+2 fashion also with Dienes, dienes can be substituted in a variety of fashion. If these are internal tethers, these can give rise to a variety of cyclic structures also. We now move on to the concerted photochemical 2 pi plus 2 pi cycloadditions. We know that 2 pi plus 2 pi thermal cycloadditions in ground state are forbidden, but they are allowed in the photochemical conditions in a superficial overlap. So a variety of reactions are known for this kind of cycloaddition. The reaction usually will occur in the excited pi star state, and usually for a triplet type of state you would need a triplet sensitizer, okay, to form the T1 kind of state. The photodimerization of a variety of non-conjugated acyclic olefins to cyclobutanones gets complicated because the electronic absorption of this chromophore occurs in a very short wavelength UV region, and the cis-trans isomerization for variety of olefins and the formation of fragmentation products will compete with the cycloaddition under the photolytic conditions. So if you consider this particular transformation, one would wonder whether this would be reversible or not. And one would also wonder, if such a strained molecule has to be formed, why doesn't it just go back to the starting material? Now the reverse reaction has to also be governed by Woodward-Hoffmann rules, right? Just like the forward one. And to go back, this four-membered ring has to absorb light. But this now has no chromophore. It cannot absorb light. It does not have any low-lying empty orbitals in which light can promote electrons. Therefore, the reverse photochemical reaction is simply not possible because there is no mechanism for this particular product to absorb light. What about the stereospecificity of cycloaddition? Now this has been very well established. For example, let us see the dimerization of cis and trans to butene. Okay, if you take only cis to butene and treat it or photolyze it, then in that particular case, the cis syn cis isomer and the cis anti-cis isomer are formed. What do you mean by this? So you can see here, this is cis, and these two are now syn with respect to each other. This is cis, this is cis, these two are now anti with respect to each other. Similarly, if you see, when pure trans to butene is photolyzed in liquid state, then you get a trans anti. So a trans anti-trans and a trans, or rather let's see it this way. Let's consider it this way. Cis anti-cis. Although the fragments that are combining are this and this. Okay. But if you see, this is similar to this fellow. Okay. When you mix them, the cis and trans to butene, and photolyze them, then you get one additional product which comes from the photocycloaddition of this. And you can see here that the stereochemistry of both is maintained. That means it is highly stereospecific and most importantly superficial in each of the reacting partner. Let's look at regioselectivity. For example, we take this alpha beta unsaturated substrate and try to treat it with this under photochemical condition. This reaction works very well and gives you this particular product. Why do we get this selectivity? Why do we not get this reverse selectivity? If one has to see then the reaction of this particular substrate under normal conditions would occur in this particular way. If you're considering the HOMO and the LUMO of this substrate, then the electron flow would be in a way that this would occur according to the arrows that are shown here, thereby leading to a positive charge which would be highly stabilized because of the two alkyl groups, and a negative charge which would be highly stabilized on the oxygen. But obviously we are not doing a thermal reaction. We are doing a photochemical reaction. In the photochemical reaction, we are now considering the enone, okay? And we are considering the LUMO of the alkene, okay? All right, so the LUMO of the enone. Why are we considering the LUMO of the enone? We are considering the LUMO of the enone because we have now excited the enone. Why we have excited the enone? Because the enone is alpha beta unsaturated. It is excited preferably in comparison with the alkene, which is not alpha beta unsaturated. So if that is excited, obviously we have to consider the LUMO of that particular species for its interaction. As you can see, the LUMO has a higher coefficient at this particular position. This will now have a higher coefficient with respect to this particular LUMO for the alkene. Okay, so this has to now be a superficial interaction. Therefore, you get this particular regioselectivity with respect to this particular example. Let's now consider an example in which trans-stilbene reacts with tetramethyl ethylene. This reaction is very facile, gives a very high quantum yield, phi equal to 1, and very high regiospecificity. It also indicates that there is an exciplex formation. Okay, what is an exciplex? Exciplex is a complex formed in the excited state. Let's see now the cycloaddition of cycloalkenes. In case of cycloalkenes, in 3 to 7 membered rings, there is no possibility of a cis trans isomerization that was possible with acyclic olefins. Why? Because the trans olefin is not stable in rings which are lower than 8 membered. Therefore, the cis trans isomerization usually does not occur under photochemical conditions in 3 to 7 membered ring systems. What does this mean? This means that the cycloaddition can now be efficient because a competing process is now not possible. Now, simple alkenes will absorb very poorly in this particular region. Therefore, as earlier also, we will need a triplet sensitizer which has an energy of greater than 75 kilocalories per mole. This is ideal to promote the sensitized reaction. Let's see some examples of concerted 2-pi plus 2-pi cycloadditions in the photochemical mode. As you can see here, this is now governed by steric effects. So in this particular case, you can see here this is an all-cis system and this is a cis-trans system. This obviously would be sterically favored. If you see here for the cycloalkene, cyclobutene, this also is giving you a cis-trans system. If you see for norbornene, then this also is preferring a cis-trans system. Okay, a trans is favored in this particular case. Okay, all right. In these type of systems, let us first see the acenaphthalene case. Okay, now this gives you the syn dimer. Why does this give you the syn dimer as against the trans dimer? In the syn dimer, we have an excited singlet state which is formed by a pi stacked excimer. Okay, in an excited dimer. So in this particular case, there is a strong secondary orbital interaction, which leads to the syn dimer being formed preferentially over the antidimer. Whereas in the triplet state, you will have a mixture of syn and anti, where the anti is now dominating. Why? Because the reactions in the triplet state usually involve the formation of biradical intermediates. Let's go on to intramolecular 2+2 cycloadditions of this kind. So you can see here, this is the formation of this highly strained molecule. This can proceed in simple photolysis or via sensitized photolysis, and the efficiency of this particular transformation is decently high. Why? Because the two olefinic bonds are now suitably disposed in the molecule. That means they are perfectly placed with respect to each other to give you a 2pi plus 2pi photochemical cycloaddition. If you have this kind of a system, this also is very facile. One would wonder why. It is because the starting material has a decent amount of strain which is released to a certain extent because the internal double bond is now lost, therefore reducing the strain to some extent, and this has been calculated to be 26 kilocalories per mole. These are other examples of formation of cage structures by photochemical cycloaddition. This is a dimer, an endodimer of cyclopentadiene. And if this is photolysed, this gives a beautiful cage structure by the reaction of these two pi systems. In this particular case, in the second example, these two pi systems are beautifully placed to give you a very nice cage structure of this kind. In a variety of steps, this can now be removed using lead tetraacetate by hydrolysis and lead tetraacetate to give you this molecule which is called as basketine because it looks like a basket. In this particular case, you can see here these two olefins react to give you this beautiful cage structure in very decent yield. In this particular case, there is a transannular cycloaddition to give you this tricyclic fused system. In the next example, you can see here this acetal reacts very well under photochemical conditions to give you a 2+2 cycloaddition followed by protic hydrolysis of this particular ketal to give you the ketone, and this in a variety of steps can be converted to this molecule which is called as pentaprismine. This particular molecule in this case reacts beautifully well. These are wonderfully placed to give you a cyclobutane by a 2+2 cycloaddition under photochemical conditions, and in a variety of steps these can be decarbonylated to give you the bis homohexaprismane. In this last example that you can see here, the hircitine, which is a natural product, can be synthesized from this particular starting material, and you can see here these two can now be fused together into a cyclobutane using photolysis. At very high temperature, this now undergoes a rearrangement reaction to give you this tricyclic fused system, which can be converted into a variety of steps into hircitine. This is the hexamethyl Dewar benzene. This can be combined into this prismane derivative using a photolytic condition in a 2pi 2pi supra interaction. What about 4pi plus 4pi supra cycloaddition. According to Woodward Hoffmann rules, obviously this would be an allowed process under photochemical conditions. Let's see some examples. In this particular case, you can see here this is a 4 pi plus 4 pi system under photochemical conditions. This reacts in an intramolecular fashion to give you this highly fused and strained system. Anthracene can be dimerized in a head-to-tail dimer or a head-to-head dimer using this particular system. Why does this reaction proceed? Because in this particular case, the resulting products have isolated benzene rings. That means they have full aromatic systems at the two ends. And probably this is the driving force for this type of cycloaddition. We will also see how anthracene behaves like a diene in the Diels-Alder 4 plus 2 cycloadditions. This is a pyridone system. So you can see here the 4 pi system can undergo a dimerization with another molecule to give you this kind of a C2 symmetric molecule of this kind by a 4 plus 4 cycloaddition. So today we saw the cycloaddition reactions, we saw the theory, and we saw some reactions of 2 plus 2 cycloadditions, and we saw a couple of 4 plus 4 photochemical cycloadditions. In the coming lecture, we will see a couple of examples of the Diels-Alder cycloadditions which fall under the 4 plus 2 thermal cycloadditions. Thank you everyone. We'll see you at the next class. Goodbye.